Hello, geometry students. Mr. Zacek back and better than ever. Here in Unit 5, we're talking about Lesson 3. We're going to look at two vocabulary terms today, the incenter and the circumcenter of a triangle. We're going to define those and look at the relationships that we can determine because of those things. And so to begin, we have this thing that says construct a ray which is the angle bisector of B. Label the points of intersection of the first arc and the sides of B, A, and C. So let's do kind of step one. That's our reference arc. So we're going to put our reference arc in here. I'm just going to go ahead and finish the angle bisector construction because we've done that a bunch, so we're pretty familiar with that at this point in the year. And we're going to come down here, put our compass point at that intersection. Okay, make that final piece here, and it says label these points A and C, and then label the point on the angle bisector D. So let's put our, kind of get our straight edge here and go through here, and we're going to label this one as, call this point D. So what do we know about every point on the angle bisector that we constructed? Well, this is our previous lesson, 5-1. We know that every point is equidistant from AB and BC. So both sides of the triangle, or excuse me, of the angle. We're going to use that information to build into some specific stuff in this lesson. Okay, now an inscribed circle is a circle inscribed in a polygon, touches each side of the polygon at exactly one point. The circle is completely inside the polygon. So when you look over here, what you're seeing is there's a point that this touches the circle, but it never goes outside of the circle. All right, so we're just building some definitions. The next phrase we have is concurrent, when three or more lines intersect at the same point. And then the point of concurrency is the point at which the lines intersect. And I've got a little song that I saying, I can't do all of it because we haven't done all the information yet, but it says, in a triangle you have three lines, and you need to know where they come together. It's the point where they meet, called concurrency, where the three lines meet together. Okay, so it's the point where they meet, called concurrency, where the three lines meet together. All right, we'll finish the rest of that in our next lesson. But today it's just, that's the idea. So the incenter, this is a new term, of a triangle is a point from which you can have an inscribe, you can inscribe a circle inside of a triangle. So the incenter is the center of an inscribed circle in a triangle. Okay, that's what the incenter is. It's that point on the inside. So let's follow along. If the circle touches each side of the triangle once, then the point where the sides of the triangle touch are each equidistant from the incenter. So this is a radius. All of these lengths are the same. They are each the length of the radius of a circle from the incenter when measured on the perpendicular. Since we know any point that is equidistant from the sides of an angle lies on the angle bisector, we can conclude that the incenter lies on the angle bisectors of a triangle. That's a key right here. The incenter, let me get a thicker highlighter. in-center lies on the angle bisectors of a triangle. So another way of saying that is the in-center is the intersection or point of concurrency of the angle bisectors. All right, so where the in-center or where the angle bisectors meet is the point called the in-center. All right, so the in-center is located by constructing the angle bisectors of a triangle. The angle bisectors of a triangle are concurrent at the in-center. Another way of thinking of that is it means they intersect at the in-center. A perpendicular must be constructed from the blank to one side of the triangle, from the in-center to one side of the triangle to determine the radius. Okay, so the theorem, the in-center is equidistant from the perpendicular segment where the circle touches the sides of each triangle. Okay, so let's walk through a couple things where we're going to put that relationship into practice. So what we see here is we have two angle bisectors and they meet. Now you don't really need the third one here, so that's kind of the first condition that is in here. All right, now we have a perpendicular line to the side from the in-center, okay, which, if my circle drawing tool will work, is going to be, so that's the in-center. So this right here is an inscribed triangle. What that allows us to do is, so therefore 2x equals x plus 3, and the reason is these are both radii, and in a circle the radiuses are all the same. So this one and this one, they're congruent, or they're the same distance to each other. So we can just go, that's why we can set them equal. So if we subtract x, we get x equals 3. Okay, so again, we saw the tick marks told us it was an angle bisector. The angle bisectors meet at the in-center. The in-center creates an inscribed circle, and we know that those two distances are equal to each other. Okay, so in number 2, this is the same thought process. So as you look at it, all right, let me get a highlighter here to help show you. So we've got angle markings that indicates angle bisector, angle bisector. We've got two angle bisectors meeting. Now it would be the same if we had all three, but we've got ourselves the in-center. And so therefore we can set these two equal to each other. So 5x minus 4 equals x plus 6. Let's add 4, subtract x. So we get 4x equals 10. So x would be 10 fourths, which would be 5 halves, or 2.5. Okay, so that's one of the ways that we can use that in-center relationship. All right, now we're going to move on to the second one for our lesson today, and it says, construct the line which is the perpendicular bisector of AB, label the midpoint as M. All right, so let's just go ahead and open this up more than halfway, above and below, make our surfboard here. Okay, above and below, and then take our straight edge and we connect those two. Again, my tool sometimes a little bit off, but we know that we've got ourselves a perpendicular bisector, and it says label this point here as M, the midpoint, and label C and D on this above and below. It doesn't really matter where those are, but we'll just put them there. Okay. So what do we know about every point along the perpendicular bisector is we know that it is equidistant from A and B. All right, this was what we studied in the last lesson. So every point is equidistant from A and B. So that means if I put some point on here, P, that means AP and BP is going to be the same distance. And if P moves up or down, that's going to be the same distance everywhere along those lines. Okay, so again, it's the perpendicular bisectors. Now this time we've flipped the diagram, and now the circumscribed circle, notice that a circle, it goes about this triangle, the polygon, and it passes through all the vertices of the polygon. So all of these points right here are on the circle. So instead of the circle being inside the triangle, now the circle goes on the outside of a triangle. All right, and we still have these things here, concurrent when three or more lines intersect at the same point, and the point of concurrency. So we've got a new vocabulary term called the circumcenter. The circumcenter of a triangle is the point from which you can circumscribe a circle around the triangle. So this point right here is the circumcenter of that. So just to summarize this quick, the perpendicular bisectors of a triangle meet at the circumcenter. And the way that I remember this is I always just think PBCC. And I'll share with you a little song later on in this unit about that, but we've got some more. Just PBCC, perpendicular bisectors, circumcenter. Okay, so if all the triangle vertices lie on the circumference of the circle, then each of the triangle vertices are equidistant from the circumcenter, and they are each the radius of the circle. So as you look at this picture here, what we're saying is all three of those segments are going to be the same length because they're all radius of this circle that we know here. So since we know any point that is equidistant from the endpoints of a segment lies on the perpendicular bisector of the segment, we can conclude the circumcenter lies on the perpendicular bisector of the sides of a triangle. So the circumcenter of a triangle is located by constructing the perpendicular bisectors of each side of the triangle. The perpendicular bisectors of the sides of the triangles are concurrent. That means they intersect at the circumcenter. So the vertices of the triangle are all equidistant from the circumcenter. All right, so on the coordinate plane, find the circumcenter. Okay, so let's think about this. Perpendicular bisectors. Perpendicular bisectors. Coordinate plane. Okay, connection. Perpendicular, you want to think slope. Bisectors, you want to think midpoint. So y2 minus y1 over x2 minus x1, x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. And we're thinking with the slopes that we want negative reciprocals. All right, now, if we have them graphed, sometimes we can just do it a little shortcut. And I'll show you in this first example. Okay, so I'm going to start off by looking at this side here. I need the perpendicular bisector. Well, the bisector needs to go through the midpoint. That's going to be the midpoint. Perpendicular, that's a horizontal line, so a perpendicular would be that line. Now let's take this line over here, this side of a triangle, and let's find the perpendicular bisector of that side. Okay, well again, the midpoint, I can just count 1, 2, 3, 4, so the midpoint is going to be 2, and a perpendicular line is going to come this way. Here's the good news. Once you've got 2 of them, you don't really need to do the third one. Okay, so we can find that the circumcenter for this, okay, the circumcenter is going to be the point -2, 2. All right, so there are some instances where we need to be a lot more like we got to do the formulas, but in this case we don't really need to do the formulas because we have all of that stuff going on. So take advantage of the horizontal and vertical lines. Number 2, we've got this line right here. Let's take advantage of that to make this a little bit easier on ourselves. So the midpoint, 1, 2, 3, 4, 5, 6, okay? Well, that means that the perpendicular bisector is just going to be along there. Now here's where it gets a little bit more involved. So now I've got, what's the slope of this line over here? Well, this point is -3, -2, and this point is 0, 1. So let's find the slope. So we've got -3, -2, and we've got 0, 1. So x1, y1, x2, y2. So the slope is y2 minus y1 over x2 minus x1. Always want to put those second ones in parentheses. 1 minus -2 is 3 over 3. So the slope is 1. That means the perpendicular slope, the negative reciprocal, would be -1. So now we just need to find where is the midpoint. So the midpoint, well, our midpoint formula says x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. The midpoint formula, that's for you. So, -3 over 2 and -1 over 2. So -1/2, -1/2. This is where the midpoint is. And now the slope is -1. So we're going to go down 1 over 1, which is going to intersect it right here. Down 1 over 1. And what it looks like then is that means that this line right here is going to intersect, and that's our circumcenter, would be the intersection of those two. Okay, so the circumcenter would be at 0, -2. All right, so both of those are right triangles, and one of the things we'll see is that the right triangles, it always happens on the right triangle, right along on the hypotenuse. Okay, that's a little, for those of you who might have noticed that, it's different when they're acute or when they're obtuse, and we'll talk more about that in the future. But we have today, just to summarize, the angle bisectors intersect at the incenter. The perpendicular bisectors intersect at the circumcenter. Okay, so good luck with your assignments. Let's keep on asking questions, and keep on. I'll see you in class.